Hello, my name is Alex Fester, and this is my digital sampling lab report. In this experiment, a data acquisition system was used to measure the signals produced by various digital and real audio waveforms. A VI was used to display the time history and power spectrum for each of the waveforms. By displaying the frequency and power of each of the modes in the signals, the frequency spectra revealed unique characteristics about the waveform content. The following tables display the results of waveform identification and signal analysis for 11 digital audio waveforms. Similarly, the following table represents the relative response of a microphone speaker system. It should be noted that the speaker seemed optimized for mid-range frequencies because very low and high frequencies output with very low volume. This caused the power recorded by the microphone to be reduced. In addition, the microphone seemed sensitive to high volumes. In contrast, a direct connection using an audio breakout jack provided constant power independent of frequency. Real-world experiment, music note frequency spectra analysis. Experimental motivation. Musical notes are common complex audio waveforms, and as a musician, I was interested in applying signal analysis to understand why the same notes on different instruments have distinct timbres. Additionally, I wanted to use the hardware and techniques learned from earlier experiments, like aliasing and filtering, to compare audio signals from real and virtual instruments. I intended to answer 3 questions. Firstly, what are the appearance and characteristics of a music note's frequency spectra and time domain? How do differences in the power spectra for the same note recorded on different instruments explain the instrument's unique timbres? And thirdly, how do real audio signals recorded from a microphone differ from digital audio signals recorded using an audio breakout jack? In summary, my experimental goals were to sample signals produced by musical notes recorded from both a ukulele and virtual piano using appropriate techniques. Then, I wanted to analyze the time histories and power spectra of the real and digital audio signals to qualitatively characterize the musical notes, to compare the power spectra of identical notes played on different instruments, and to evaluate the recording performance of both the microphone and the audio jack breakout. Approach, materials, and procedure. This slide lists all of the materials that were used in this experiment. Note that the ukulele was used as a real instrument and that an iPad was used as a secondary audio output device to play a virtual piano. Experimental procedure. The procedure essentially consisted of first configuring the lab jack DAC as well as the VI. Then, a particular set of notes was played on the ukulele and recorded using a microphone. The hold function within the VI was used to save the time history and power spectra for each note. The power spectra and time history for the same notes were also recorded for the notes played on the virtual piano. Configuring the DAC, complications and mitigation strategies. A high-pass filter with a cutoff frequency of 10 Hz was implemented to attenuate a DC component of 2.5 volts magnitude that was created by the microphone as seen on the right side image and left side image. Additionally, I discovered that musical notes have harmonic modes with significant power up to frequencies of roughly 3,000 Hz. Therefore, to prevent aliasing, the sample frequency was set to roughly 6,000 Hz. Raw and reduced data. The raw data consisted of 8 text files and 8 screenshots containing the time history and power spectrum for the 4 notes played on both the ukulele and piano. Data reduction. For each text file, the following were identified and tabulated: the peak frequencies, the corresponding powers, and the corresponding powers normalized to the fundamental frequency, which was conducted by dividing the power at each peak frequency by the power of the fundamental frequency. In addition, for each musical note, the normalized power versus frequency for both instruments were plotted on the same plot. These plots are called normalized power spectra or relative power spectra. The following slides show the reduced data for each of the 4 notes. This is for the C4 note and the normalized power spectra. This is for the G4 note. This is for the E4 note. And this is for the A4 note. Conclusions. The time histories indicate that musical notes have periodic signals and that they consist of fundamental frequencies with higher order harmonics. The time histories depict sinusoidal waveforms which are imperfect. This is because the higher order harmonics create jagged edges and complex slopes. Critically, the frequency spectra show that the fundamental frequency and harmonics are identical for the same note played on different instruments. This makes sense and was expected because ultimately the fundamental frequency is what identifies a particular note. Interestingly, the normalized power spectra show that the relative power of higher harmonic modes differ between instruments for the same note. This means that while the ukulele and piano share the same frequencies for each note, The harmonics contributions to the overall sounds in the notes differ, which can be seen in the table on the right. To answer my earlier question, the timbre of different instruments vary for the same note due to differences in the relative strengths of the note's higher order harmonics. Higher order differences also explain the differences in the waveforms in the time domain, as seen on this previous slide. Finally, consider the normalized power spectra for the G4 note. Evidently, the ukulele signal is far more irregular and noisy. This noise can be characterized as white noise because it is constant with frequency. The noise could have been caused by ambient noise from the environment, echoes or room acoustics, or even microphone sensitivity. In contrast, the audio jack signal is isolated from interference. This means that it might provide more high-fidelity data for certain applications, which should be kept in mind. Thank you for listening.